Here comes the basic structure of JFET, and it is a NJFET. So here will be three parts as usual: drain, source, and the gate part. Being the NJFET, so the major part of it is N, and the other two parts are P. And as it is P and N, there will be depletion region as usual. And what we can understand by source, gate, and drain. The gate is the controller of flowing something. It may be water, it may be voltage, it may be current from source to drain. So gate is controlling all over. Now consider this. Uh, in this region, we can see that the upper side, what do you call, the depletion layer is higher than the lower part. And but why this happened? So here we make a different change. As G and S, there will be zero voltage, that means there will be no voltage difference, and IDS, there will be a voltage called VDD. So the higher voltage is provided here. This voltage will be decreasing in the way of go down. So in this region, this voltage will get lighter or smaller. So we can consider this. Imagine VDS is 2 volts, so here is 2 volt applied, but uh, in this sector there are resistance, so the voltage will fall apart, and this voltage will turn into 1.5 volt here, 1 volt here, 0.5 volt here, at last 0 volt here. So you see, as VGS, this part is 0 voltage, then in the upper region the voltage difference here is 1.5 volt, but in the lower region this voltage difference is 0.5 volt. That means here upper voltage drop happened. So as this is reverse bias, so the depletion region will get wider, and that's why it is wider than the lower side. And what will happen if we increases VDD, keeping GS as 0 voltage? So if we increase VDD at a level of VP, then these two parts will almost come closer. At a point we can consider that this is almost touchable, but it's still not touchable, because there will be still a thin narrow path of going electron in the downside. But in that case, the resistance density here will be get higher, so at last the current flowing from here will be come to a saturation level, which is called IDSS. So when IDSS will happen, then how much you increases the VDD or more than VP you use, that will not change the amount of ID. That means IDSS will be the same. So here we go, see a chart or graph. So this graph shows this from 0 to VP, that is pinch of voltage. This increases as usual ohmic structure, ohmic graph. But when it comes to the side of VP, then the current has suddenly became constant, and it continues to be IDSS. So this graph is for VGS is 0 voltage, but what happened if we decreases the VGS voltage by 1 minus 1 volt or minus 2 volt or minus 3 4 volt, or at a certain instance VP4? So how much we decrease VGS, then the IDSS will be get also decreased. So in this point, when VGS is minus 2 volt, we get IDSS at a level of 2 milliamperes. That means the IDSS will be less. So we can control IDSS, we can ensure we can go through our you know what we expect IDS by changing VGS as value. but when it comes to a voltage of Vp, that means minus Vp, then there will be a cutoff effect. In this case, these two portions will absolutely touch each other and no ID will be followed. So that's what happened here. Here is ID and IDSS, both are